Atmospheric rivers, narrow corridors of concentrated moisture that transport water vapor from tropical regions toward mid-latitude coastal areas, have historically impacted western Washington with increasing frequency and intensity. These weather phenomena typically form when warm, moist air masses from the Pacific Ocean encounter cooler continental air, creating conditions conducive to heavy precipitation. The earliest documented atmospheric river events affecting Washington state date to the mid-20th century, though systematic tracking began in the 1990s with the advancement of satellite technology. Between 1950 and 2000, Western Washington experienced approximately 10 to 15 significant atmospheric river events annually, with precipitation averaging 2 to 4 inches per episode. From 2000 to 2020, this frequency increased to 15 to 20 events per year, with average precipitation rising to 3 to 5 inches per event. The economic impact of these events has grown substantially, with damage costs escalating from approximately $50 million annually in the 1990s to over $200 million annually in the 2010s. Power outages affecting more than 100,000 customers occurred approximately once every 3 years before 2000, but increased to once every 1.5 years between 2000 and 2020. The December 2007 event caused $1 billion in damages and affected over 1.5 million residents across Western Washington. By 2025, atmospheric rivers are responsible for approximately 30 to 40% of the region's annual precipitation, with extreme events increasing by 25% compared to the late 20th century. Projections through 2050 indicate a further 15 to 20% increase in intensity and frequency, with potential economic impacts exceeding $500 million annually if adaptation measures are not implemented. Benefits include substantial water replenishment for reservoirs and snowpack, critical for the region's water supply and hydroelectric power generation. Drawbacks consist primarily of infrastructure damage, transportation disruptions, and increased landslide risks in mountainous regions. Future optimization strategies include improved forecasting systems using AI algorithms, enhanced grid resilience through underground power lines in vulnerable areas, and expanded green infrastructure in urban centers to manage stormwater runoff.